Section 8.3, Simplifying Radical Expressions. Alright, so we're now going to look at some examples in this section where we have to break down radicals or we do some operations with radicals. First thing we're going to look at is when we're multiplying two different radicals. So we have the product rule we'll talk about, and we're going to derive that first. And I'm asking you this question. Does the square root of 9 times the square root of 4 equal the same thing as if we multiplied 9 times 4 and then took the square root? So let's break it down both ways and see if we get the same answer. If we were to take the square root of 9, we would get 3. If we were to take the square root of 4, we'd get 2. Does that equal the same thing as if we square rooted 9 times 4, or 36? Okay. Well, 3 times 2 gives us 6, and on the other side, the square root of 36 is 6. So yes. Does it give us the same thing? Sure does. So that brings us to this idea of the product rule that kind of develops the product rule, which is that if we take the root, a certain kind of root, an nth root of some value a times the nth root of some other value b, it equals the nth root of their product. So the important thing to keep in mind here, though, is it needs to be the same kind of root. Okay? It needs to be the same kind of root. That's why it has the little nth root symbol above it. Okay. So applying the product rule here, we have the cube root of 5 times the cube root of 7. Because those are both cube roots, we can go ahead and combine them into one single root. This is going to equal the cube root of 5 times 7. Probably should add 2. You can't cube root 5 and you can't cube root 7 because neither of them have a number that cubed would get you 5 or a number that cubed would get you 7. However, we can combine in this way. Multiplying 5 times 7 would get us 35. So we have ourselves the cube root of 35. And there's no number cubed that gives you 35, so there's nothing we can do with that expression. We'd have to just leave it like that. Okay, next example, we have the square root of 11 times the square root of p. They're both the same kind of root. They're both square roots, so we can combine this. This is going to equal the square root of 11 times p, or in other words, the square root of 11p. Okay. But 11 is not a square. You can't square root 11, and p is not to the second power, or a power that could be divided by 2, so there's nothing more to break that one down. Alright, next example, we have a 6th root of 10m to the 4th times another 6th root of 5m. They're both the same kind of root in that they're index 6, so we can combine these. This is going to equal the 6th root of 10m to the 4th times 5m. Okay. Multiplying 5m times 10m to the 4th is going to give us 50m to the 5th. So we have the 6th root of 50m to the 5th. Okay. And we cannot take the 6th root of 50. There's no number to the 6th power that would give us 50. And we can't take the 6th root of m to the 5th either. If we had m to the 6th, we could 6th root it, and that would kind of cancel out the power and the root. But nothing to do there. In our last example, we have a square root of 2, and we're trying to multiply that by a cube root of 2. Now they have the same value inside the root, okay, kind of the same base, we could call that, but they're different kinds of roots. One's a square root, one's a cube root. So because of that, we can't simplify. because they're different roots. Okay. Remember, square rooting from the last section would be like taking something to the 1/2 power, and cube rooting something would be like taking it to the 1/3 power. So that would be like trying to combine 2 to the 1/2 power times 2 to the oh, sorry, I'm kind of getting ahead of myself. That'll be another way we can combine these later. Okay. So that's the product rule, okay, when we're multiplying two radicals. So now we're going to look at, what about other types of expressions? What about if we're dividing things? Is there a quotient rule we could put into place that'll allow us to simplify radicals when we're involving fractions? So take a look at that now. The quotient rule for radicals. If we take the square root of something like 16 over 25, is that equivalent to taking the square root of 16 over the square root of 25? So in other words, applying that radical to your numerator and denominator first, rather than taking the fraction first and then applying the radical. So if we were try to break this down, if we square rooted 16 and 25, we would get 4 over 5. Not 4 over 4, 4 over 5. And I guess really the only way to check is 4 over 5. If we square that, will it get us the value underneath that radical? And if we squared 4/5, that gives us 4/5 times 4/5 would get us back to 16/25, which is the value under the radical. Okay. Or if you took 16 over 25, took that to a decimal, and then square rooted that, it should give you the same decimal 4/5 would, which is 0.8. Okay. So in this case, we do have a quotient rule that will apply. So in more general terms, if we take the nth root of a fraction, it's equivalent to taking the nth root of the numerator over the nth root of the denominator. So we can try to apply that now to our two examples. Again, because this checked out. So we'll look at the cube root of 7 over 1/25. Okay? That'd be kind of an odd thing to try to cube root as a fraction. However, we can break it down into the cube root of the numerator, cube root of 7, over the cube root of the denominator, 125. So now if either of these two values are cube rootable, or both, then we want to go ahead and simplify those. We cannot take the cube root of 7, so that has to stay, cube root of 7. But 125, we can take the cube root, because 5 cubed will give us 125. So the cube root of 125 is 5. Okay, 5 times 5 times 5 would give us 125. So that expression would simplify into the cube root of 7 over 5. And the last example on this page, we're taking a fourth root. So we have negative fourth root of m to the 8 over 16. So how can we break this down? Well, the negative will still be out front, but we want to take the fourth root of m to the 8th power over the fourth root of 16. Okay. Now m to the 8th power, can we fourth root that? If you remember from our last section, whatever our power is, we can take that as the numerator of our fraction exponent, and whatever the root is becomes the denominator of our fractional exponent. So if you don't recall that, this is what I'm talking about. If we have the fourth root of m to the 8th is like taking m to the 8 over 4 power. We can turn a root, a radical, and a power situation into a fraction. And 8 divided by 4, because 4 divides 8, then we can turn that into a whole number exponent. Down below, we can take the fourth root of 16. 2 to the fourth power gives us 16. So the fourth root of 16 is 2. 2 times 2 times 2 times 2 gives you 16. So just one more step, simplify that fraction. So we get negative, we have m to the second power. Okay, 8 over 4 is 2. And all over 2. So we already simplified that denominator. Okay. So that's applying the product and quotient rule, and that is going to now help us to simplify some of these radical expressions, or multiplying things, dividing things, or even just trying to simplify a radical as it is without any operations. So we'll look more at that here on the next page, the notes. Okay, continuing though still, section 8.3. We're going to look at simplifying some roots now. So a couple rules. Just like simplifying a fraction, okay, kind of the same idea, or simplifying an expression with an exponent, we might get a situation where we can't take a certain root of a number, or even a certain root of a variable. However, we can break the expressions down into factors that could be rooted. And also, another rule, we're not fully simplified until our exponents, they must be less than the root, or the index. So whatever power we have on our variables has to be less than the type of root we're taking. Otherwise, it's not fully broken down and simplified. Alright, so we have to keep those two things in mind when trying to simplify these expressions. First example, we have the square root of 24. Well, we can't square root 24. It's not a perfect square. Okay, 4 squared gives you 16, 5 squared gives you 25, 24 is not a perfect square. However, we can think of breaking 24 down into possible factors where at least one of those factors could be square rooted. Okay, 24 equals 2 times 12, but that doesn't help us because neither 2 nor 12 could be square rooted. However, another way to break down 24 would be 4 times 6. Now 4 can be square rooted, that's a perfect square, so that's how we'd want to break this down. We're kind of going in the opposite direction of the product rule we just looked at. Product rule told us the square root of 6 times the square root of 4 would give us the square root of 24. However, we want to break square root of 24 down this way so that we can square root something. So the 4 could be square rooted, gives us a 2. So we have 2 times the square root of 6, which we just write as 2 square roots of 6. And that's how we would read it. Okay, whatever can't be rooted stays underneath the radical symbol. Whatever you can square root, you want to pull out front. Now with the 6, you could break 6 down again into 3 times 2, but neither of those values can be square rooted. So there's nothing more we can do here. Okay, that's when you know to stop. Alright, next example. Now we don't have a square root, we have a cube root. There is no number cubed that will give you 16, or negative 16 for that matter. Okay, 2 cubed gives you 8. 3 cubed, 3 times 3 times 3 gives you 27. So no number cubed will give us 16. However, 16 does have a factor that could be cube rooted. We just talked about it, 8. So we could break this down. Instead of the cube root of negative 16, we could break this down into the cube root of negative 8 times 3. Times 2. And you could have just split it up, done this in the first step. The cube root of negative 8 times the cube root of 2. Remember, we can cube root a negative because a negative times a negative times a negative will give us a negative. Can't take a square root of a negative, but we can cube root one. So what number times itself again gives us negative 8? Well, that would be the cube root of negative 8, which is negative 2. Okay. Whereas the cube root of 2, we can't take that. There's no number cubed that gives you 2, so that 2 has to stay inside the radical. So we would read that as negative 2 cube roots of 2. Okay. Alright, now we'll look at a little bit more detailed, a little more difficult examples. We have the square root of the expression 200k to the 7th q to the 8th. So this is going to equal square root of 200. Well, we can't square root 100, but we can't square root 200, but we can take the square root of 100, okay, times, we can then break that down into the square root of 100 times 2, okay, because that will give us 200, and 100 can be square rooted. You could have also done, let's say, 25 times 8, because 25 could be square rooted. However, you want to take the biggest one value that could be square rooted, otherwise you're going to have to reduce again. Just like with a fraction. If you don't reduce a fraction with the largest factor, you're going to have to reduce again. So 100 is the biggest factor of 200 that can be square rooted. So you want to take it that way. Now here's where it gets interesting. We have k to the 7th and q to the 8th. We cannot leave those as k to the 7th and q to the 8th because our exponents are larger than our power, our index. Remember, a square root is actually like taking a root of index 2. And so since our root 2 is less than our power, we're not okay. Our exponents must be less than the root when we're fully simplified. And right now our exponents are greater than the root 2. So what we want to do is break down k to the 7th in terms of two different powers of k, one of which could be square rooted. So remember, when we square root something, we make it a fraction over 2. The root would be the denominator of the fraction. The numerator would be our power. So what we want to do is break k to the 7th down in terms of the highest even power of k. So k to the 6 is as close as the largest even we can get without going over 7. And then, so that it still equals k to the 7th, we would need one more power of k. So k to the 6 times k would give us k to the 7th, but we're going to be able to take the square root of k to the 6 because that's an even number, and we can divide 6 by 2. On the other side, with k to the 8th or q to the 8th, that is already an even power. So we're going to end up turning that root and that power into a fraction, and we can divide 8 by 2. So we're going to be okay there. If that didn't make sense, watch what I'm doing on this next step. This should hopefully clear it up. Okay. So the square root of 100 is 10. We cannot take the square root of 2. Nothing else to break it down into, so keep it square root of 2. Now, the square root of k to the 6, remember we can turn this into a fraction. That would become the power 6/2. Okay? The power is our numerator 6, the root 2 is our denominator, so 6 over 2. We can't square root k. This one's simplified because our power 1 is less than our root 2. So that's good, that's fully simplified there. And then q to the 8th, well, the square root of q to the 8th we can rewrite as q to the 8 over 2 power. So you see there, by breaking down our variables so that they have even powers, now we can square root them because we can divide an even power by 2, which is what you're doing when you're taking a square root. So this is going to equal anything that could break down we can put out front. So the 10. 6 divided by 2 gives us 3, so we're going to have k to the 3rd. And then over here, q to the 8 over 2 gives us 4, so q to the 4th. Anything that we could actually take a root of, square root of, we throw out front. But then the square root of 2 and the square root of k, we could not do anything with those. So we want to keep a 2 and a k underneath that root. So we have 10k to the 3rd, q to the 4th, square roots of 2k. And now underneath that radical, k is to the 1st power. It's a square root, in other words, index 2, so we're good. We're fully simplified. Alright, so that's how we're going to want to look at these things. Next example, cube root of negative 54, x to the 4th, y to the 5th. To break these down, we're going to try to, if we can cube root 54, great. If not, break it down in terms of factors that could be cube rooted. But then with x to the 4th and y to the 5th, we have to break down those powers of x and y into some power that could be divided by 3 now, instead of being divided by 2. because in the example above we had a power of a root of 2. Now we have a root of index 3. So we cannot actually take a cube root of negative 54. However, one factor of 54 that can be cube rooted is 27. So we can pull out the negative 27 and cube root that, times we can cube root what you'd have to multiply that by, so 27 times 2, or negative 27 times 2. So we have to cube root those two things, and now we want to break down x to the 4th. Since we're cube rooting it, we want to break it down into terms of something that could be divided by 3. So x to the 4th is the same thing as saying x cubed times another x. So we're going to have the cube root of x to the 3rd times the cube root of x. Okay. And we want to do the same with y to the 5th. Y to the 5th we could break down into y to the 3rd times a y squared. So we're going to take the cube root of y to the 3rd times the cube root of y squared. Okay. Now we start simplifying. Cube root of negative 27 gives us negative 3. The cube root of 2, can't do anything with that. That remains cube root of 2. When you take the cube root of x cubed, that would be like x to the 3 over 3 power, or x to the 1st, which is just an x. Or remember it as the cube root of something cubed. We'll just cancel out the root and the power and just give you x. Okay. The next part, the cube root of x, well, we can't do anything there. X is technically to the 1st power, and our power is then less than our root, so we're good there. Same idea here, cube root of y to the 3rd. Well, our cube root and our cube cancel each other out. That leaves us just y. And now here, our power 2 is less than our root 3, so there's nothing to do to simplify there. Go back up to our rules up here. Exponents must be less than the root. Well, here our exponent y squared 2 is less than our root 3. So you can't simplify. You're good at that point. So now let's just clean this up. Everything that could be cube rooted you write out front of the radical. So the negative 3, the x and the y. Those all go out front. And then we have a cube root of 2, x, and y squared. So we throw all that back underneath the radical in one single radical. So 2x and y squared. So some of the x's we are able to pull out front, the negative 3 and the xy, and then we have a cube root of 2xy squared. Okay. And last example, we'll look at a fraction, so we can apply the quotient rule. So here we have the square root of x to the 13th over the square root of, over 144. So we can break this down into two separate square roots, applying that quotient rule. So square root of x to the 13th over the square root of 144. Okay. Well, can we square root x to the 13th? No, because that's the 13th power is an odd number. And a square root is a root of index 2. So whatever power we have on x needs to be divisible by 2. So let's break down x to the 13th as the square root of x to the 12th times another square root of x. Okay, x to the 12th times x would give us x to the 13th, but we can square root x to the 12th since that's an even power that we can divide by the root 2. So then denominator, we have the square root of 144. Alright, so now let's simplify. X to the 12th is equivalent to saying x to the, or the square root of x to the 12th is like saying x to the 12 over 2 power, times, we cannot square root x since that doesn't have a power of 2, or something higher than a power of 2. But we can square root 144, that gives us 12. So last step, write the final answer. 12 over 2 will divide to give us x to the 6. So x to the 6 square root of x all over 12. And that'd be our final answer. So that last example concludes section 8.3.